Okay, so in this video, we're going to take a look at the AQA June 2017 paper 1 for the AS exam. So first of all, starting with some particle physics, we've got a decay of particle X into particle Y, and we've got the quark structure shown on the diagram. So we want to deduce the name of particle X. Well, it's an up and two down quarks, so that's clearly a neutron. And it's clearly decaying into a proton because the Y is up, up, down. So a decay is caused by the weak interaction. So the W minus is a specific type of particle, and it's a type of boson or an exchange particle that mediates the weak force. Okay. So show clearly how charge and baryon number are conserved in this interaction. You should include reference to all the particles, including quarks, in your answer. So first of all, looking at charge number, we've got a neutron turning into a proton, electron, and an anti-electron neutrino. An up quark has a charge of 2/3, a down quark charge of -1/3, and an electron has a charge of -1. But both sides end up having a total charge of 0, so charge is conserved. Doing the same with baryon number, a quark has a baryon number of 1/3, so a neutron has a baryon number of 1, a proton has a baryon number of 1, electron and neutrino are leptons, so their baryon number is 0, so 1 goes to 1, so that's conserved. Okay, so name the unstable baryon. Well, we can see it from this process. Eventually, all baryons would like to become protons, but in order to form stable nuclei, we need the neutron around as well. A muon is an unstable particle. State the names of particles that are produced when a muon decays. Well, it's got to produce leptons because otherwise it would not be conserving baryon number. But it's going to produce an electron because it's got to produce lower mass particles. So it's going to produce an electron, an anti-electron neutrino to make sure electron-lepton number is conserved, and a muon neutrino to ensure that muon-lepton number is also conserved. Okay, so moving on to some electricity. So we've got an IV characteristic for a resistor and for a filament lamp. Explain in terms of electron motion why an IV characteristic for the filament lamp is a curve. So the first thing is at a high current, you get a large dissipation of heat by any component, which means the temperature of that conductor is going to increase. And when the temperature increases, the lattice atoms, or the atoms which make up the structure of the conductor, will vibrate with a larger amplitude because they have more energy. And then that's going to mean there are more collisions between the electrons and the lattice atoms every second, which means there's a larger resistance force, which is why the gradient of the graph is decreasing, showing a higher resistance. Okay. So then determine the resistance of the resistor. So we're going to want to look at the gradient of the graph, but using Ohm's law, we can see that the gradient is equal to 1 over the resistance. So we're going to find the gradient using as much of the graph as possible, do 1 over that, and we get a resistance of about 15 ohms there. The resistor and the filament lamp are connected in series with a supply of variable EMF and negligible internal resistance. Determine the EMF that produces a current of 0.18 amps. So to get the potential difference across the resistor, we can use Ohm's law. So we know the current and we know the resistance. That gives us the potential difference across the resistor. Or we could have just read it off the graph if we want to. From the graph, we can see that for a current of 0.18, the potential difference needs to be 0.8 volts, giving us a total EMF of 3.4 volts. Okay. So the resistor and the filament lamp are now connected in parallel. Determine the resistance of the parallel combination when the EMF of the supply is adjusted to 4 volts. So because they're in parallel, there are going to be 4 volts across both components, which means we can read straight off the graph what their currents are, giving us a total current through the cell of 0.63. And if we know the EMF and we know the current, we can work out the total resistance. Okay. So the resistance of the filament lamp at its working temperature is 14 ohms. The filament has a length of 0.36 meters and a diameter of 32 micrometers. calculate the resistivity when the lamp is at its working temperature with an appropriate unit. So this is the equation for resistivity. So we need to make resistivity the subject. The cross-section area is pi d squared over 4. So we can plug the numbers in and we get 3.1 times 10 to the minus 8 ohm meters. So moving on to question 3, we've got an electric wheelchair powered by a battery. So the wheelchair itself has a mass of 55 kilograms and the maximum distance it can travel is 12 kilometers. When carrying a user of mass 65 kilograms and traveling at its maximum speed of 1.5 meters per second. The battery has an EMF of 12 volts and can deliver 7.2 times 10 to the 4 coulombs as it discharges. Show that the average power output of the battery during its journey is about 100 watts. Okay, so the first thing I'm going to figure out is how long it will take. So we know the distance, we know the time, we're assuming the velocity is constant, so it's going to take 8,000 seconds to travel that far. We can also calculate the work done by the EMF source by doing the charge times the potential difference. And once we've got work done and we've got the time, we divide those, we can get the power as 108 watts, which you can see is roughly 100. So during the journey, forces due to friction and air resistance act on the wheelchair and its user. Assume that all the energy available in the battery is used to move the wheelchair and its user during the journey. Calculate the mean resistive force that acts on the wheelchair and its user. So it's not going uphill, so we don't have to worry about GPE. It's a constant speed, so we're not increasing kinetic energy. So the work done must be just equal to the work done against frictional and resistive forces, which if we divide that by the total distance will give us the average resistive force. So the wheelchair is now going uphill at an angle of 4.5 degrees. Calculate the force that gravity exerts on the wheelchair and its user parallel to the slope. So we want mg sine theta. The total mass is 120. It's 65 plus 55. Then we just plug the numbers in and we get 92 newtons. Calculate the maximum speed of the wheelchair and its user when traveling up this hill when the power output is 100 watts. Assume the resistive forces of friction and air resistance are the same. So we're going to use P equals FV. So to get max velocity, we're going to put in the power and the force. The total force will be the 92 against the weight force and 72 against resistance, giving us a velocity of 0.61 meters per second. Explain how and why the maximum range of the wheelchair on level ground is affected by the mass of the user and the speed at which the wheelchair travels. So we'll do the mass first of all. So things with more mass have a higher friction because that makes the normal contact force bigger, which is one of the factors that affects friction. So if friction is bigger, that's going to have a bigger resistive force, so you're going to travel a smaller distance. Speed is similar, so higher speed means you have bigger air resistance, and that's going to mean the wheelchair has a smaller maximum range. Moving on to question 4, looking at some double slit interference. We're doing it with microwaves, and we've got a microwave detector to find our maxima and our minima. And what we can see on the diagram is we've got D shown, which is the second maxima, and we've got the two path lengths from the two slits. Okay, so the microwaves are polarized, and the detector rod is in the right plane to be detecting them. And A is the line that's moving along, and we get maximum at B, C, and then D, which is the one we can see. And we've got the information that we saw from the diagram. Okay, so explain why the signal strength falls to a minimum between B and C and between C and D. So what's happening is two waves are meeting with a path difference that is an odd multiple of half the wavelength, which means they arrive in antiphase or a phase difference of pi, and therefore destructive interference occurs, creating a minimum. So determine the frequency of microwaves that are transmitted. Well, we've got two path lengths, so we can figure out the path difference. And since D is a second order maxima, we know the path difference is 2 lambda. So that allows us to figure out what the wavelength is, which then using the wave equation, we can turn that into the frequency. Okay, so the intensity of waves passing through each slit is the same. Explain why the minimum intensity between C and D is not 0. So the key here is they've traveled different distances to get to where they meet, and that means the intensity of them is going to be different, because if you travel further, you've had a longer distance for the intensity to decrease. So because their intensities are not the same, they are not going to completely destructively interfere, as their amplitudes are different sizes, and that's going to mean the intensity is non-zero in the end. Okay, so the vertical aerial is placed at position B and rotated slowly through 90 degrees until it lies along the direction AE. State and explain the effect on the signal strength as it is rotated. So, because the microwaves are polarized, rotating the detector 90 degrees will cause the intensity to decrease, but when it gets to 90 degrees, it will read 0, as the detector is now 90 degrees to the plane of polarization of the microwaves, so it detects nothing. So moving on to 5, so we've got a horizontal copper aerial wire used for transmitting radio. The wire is 12 meters, we've got its cross-sectional area, we've got the tension, and we've got the Young modulus. Okay, so the extension is about 4 millimeters. So I'm going to use Young modulus is stress over strain, stress is force over area, strain is extension over original length. Rearrange that to make extension the subject, plug the numbers in, and it comes out as 3.1 millimeters, which is clearly less than 4 millimeters. Okay, so the cables support each mast at an angle of 65 degrees to the horizontal. Calculate the tension in each supporting cable so that there is no resultant horizontal force on either mast. So essentially that means they have to be identical, and we know the tension in the horizontal part is 500, so the tension times cosine of 65 must be equal to 500, giving us a tension of essentially 1.2 kilonewtons. So when the wind blows, stationary waves can be formed on the aerial wire. Explain how stationary waves are produced and why only waves of specific frequencies can form on the aerial wire. Okay, so the oscillations are caused by the wind, and they travel along the wire and they get reflected off one of the fixed ends. So you've got two progressive waves traveling at the same speed in opposite directions, same wavelength frequency, and a very similar amplitude, as long as they haven't lost too much energy, which are going to superpose and create a stationary wave. We've got classic conditions for a stationary wave here. So the reason we can only form certain frequencies is because we've got two fixed ends. So fixed ends have to be nodes because they're fixed and can't move. So that only allows you to have certain wavelengths or certain frequencies of stationary wave. Okay. Calculate the mass of a 1 meter length of the aerial wire if the density is 8,900. So I'm going to do this. So we're effectively calculating the mass per unit length here, which is calculated by doing density times cross-sectional area. So each meter weighs 0.14 kilograms. So then calculate the frequency of the wave when the third harmonic is formed on the aerial wire. So this is the equation that links frequency, length, tension, and the mass per unit length that we just calculated. But it calculates the fundamental frequency. So when we plug the numbers in, we need to multiply that by 3 to figure out the third harmonic. Okay, so sketch on the diagram the standing wave on the wire when the third harmonic is formed. So this is a bit rough, but this is essentially what we should be looking at. We've got 1.5 wavelengths. High winds produce a large amplitude of vibration of the aerial wire. Explain why the wire may sag when the high wind stops. So the reason I think this is because we've gone past the elastic limit, so we've left the material permanently stretched, even once the force is removed, so that's why it sagged instead of being taut. Okay, so which statement suggests that electrons have wave properties? Photoelectric, no. The fact that electrons are emitted when they're ionized, no. Dark rings and diffraction, yes. Diffraction is a wave property, so that will be it. Okay. So in a discharge tube, a high potential difference is applied across a hydrogen gas contained in the tube. This causes the hydrogen gas to emit light that can be used to produce a visible line spectrum that we can see. So you can see certain wavelengths are produced. The visible line spectrum in figure 8 has been used to predict some of the electron energy levels in a hydrogen atom. So that's what we're looking at here, the different energy levels from those wavelengths. Okay. So calculate the energy in EV of a photon of light that has the lowest frequency in the visible hydrogen spectrum. So what we need to do is we're going to take the longest wavelength, that would be the lowest frequency, plug that in, gives us an energy in joules, divide that by 1.6 times 10 to the minus 19, converts it into electron volts. Okay, so identify the state of an electron in the energy level labeled 0. That's in an ionized state, which means it's basically no longer inside the atom. The state that is labeled minus 13.6, that is ground state, or the lowest energy state. Explain why the energy levels are negative. Well, it's because you have to put energy in to cause an electron to be emitted. So that's why all the electron energies are negative. Okay, so discuss how the discharge tube is made to emit electromagnetic radiation of specific frequencies. In your answer, you should explain why there must be a high potential difference across the tube, discuss how the energy level diagram predicts the spectrum shown, and show how one of the wavelengths is related to two of the energy levels in the diagram. So let's start off with the first part. So we need a high potential difference to accelerate electrons to high kinetic energy, so that when they collide with orbital electrons in the hydrogen gas atoms, they can cause them to become excited. You need quite a lot of energy to do that. So the photon energies are essentially decided by energy gaps. So the different energy gaps produce the different photon energies, and that is those photon energies produce the certain wavelength of photons. And the energies from the diagram are all the visible ones. So looking at a specific one, so if we go between these two energy levels, the one at 1.51 and 3.4 electron volts, that allows us to calculate a photon energy, which we can then see is the 658 nanometers, which is clearly in the visible spectrum and clearly one of the ones on the diagram. Okay, so that completes this AS paper.